In the previous modules in this series, we have looked at the construction and operation of the major components of the power plant, that is the boiler, the turbine, and the generator. Now it's time for us to move on and study the various systems and auxiliaries which are needed to interconnect to the major items of equipment and also to provide support services. Plant systems and auxiliaries consist of a vast array of pipework, valves, heat exchangers, pumps, compressors, and other devices, all connected in such a way as to provide for specific functions and needs. In this segment, we'll look at the various steam systems comprising A, the main steam supply from boiler to turbine, B, the reheat steam, C, the extraction steam from the turbine, and D, the auxiliary steam system. In many industrial installations where steam is employed, the boilers feed into a common header like this. Steam then flows from the header to the various items of plant, such as dryers, digesters, turbine-driven pumps, and perhaps a turbine generator. In this arrangement, the steam pressure will be relatively low, say 250 to 500 psi. Each boiler is fitted with a non-return or check valve to allow boilers to be floated on or off the header to meet steam demand. Stop valves are fitted in each boiler to permit them to be isolated at times when maintenance is to be performed. Nowadays, it is more likely that an industrial installation will include a back-pressure turbine or pass-out turbine like this. In this case, one single boiler feeds each turbine, and the pressure is likely to be about 1,200 to 1,500 psi. Steam exhausting from the back-pressure unit or extracted from the pass-out unit feeds into the common header, which then supplies the industrial process. Where the plant is devoted to the production of power only, it is normal for each turbine to be supplied from its own individual boiler, so forming an individual boiler-turbine generator unit. The main steam circuit is relatively simple, with one line passing from the boiler outlet to the turbine inlet. For a modern power plant, the steam pressure will probably be within the range of 1,800 to 2,800 psi. In order to withstand this high pressure, the walls of the pipework must be thick, perhaps 2 to 3 inches, depending upon the pipe diameter. The steel alloy materials containing chrome and molybdenum are selected to withstand the stresses imposed by the high temperature operation. A thick layer of heat insulation is placed around the pipe to prevent heat loss to atmosphere. Note the valves which are installed in this system. In this particular boiler, we have a stop valve located at the steam exit. In many cases, this valve is omitted and steam passes directly from the boiler down to the turbine's stop valve, which provides the turbine protection by closing automatically in case of a turbine trip. In this module, we'll be looking at the situation in which the boiler stop valve is installed. Once the turbine stop valve is open, steam passes into the steam chest, and from here it is admitted into the turbine through the control valves. During a cold start of this unit, we would need to charge the main steam line from the boiler stop valve down to the turbine stop valve. However, with steam pressure on one side of the valve at, say, 900 psi and 0 on the other, we would find it quite impossible to open this large valve. To overcome this problem, 1 or 2 small bypass valves are fitted, say 1 inch in diameter. Due to the much smaller face of this valve, it can be opened to allow steam to enter the main steam line. Initially, this steam line will be cold and the steam will obviously condense. This condensate must be removed through the drain lines, which are fitted at low points on the line, including just before the turbine stop valve. Initially, water will discharge from the open drain lines, but eventually, as the piping warms up, this will turn to vapor as less condensate is produced. The drain valves can then be closed, except the before stop valve drain, which should be left partially open. During this time, the pressure in the pipework should be building to a level equivalent to the boiler pressure and allow the boiler stop valve to be opened. This maneuver cannot be accomplished too quickly, as we must allow time for the pipework to heat at a reasonably unified rate. The whole operation could take as long as 45 minutes or more. A similar procedure must now be adopted to charge the turbine steam chest. That is, by opening the turbine stop valve bypass. We have already discussed this procedure in the module on turbine operation. The most important thing in this maneuver is to make sure that all of the water is discharged from the drain lines to prevent any water from being carried along with the steam and damaging the turbine when we start up. The piping must undergo considerable expansion as its temperature is raised from, say, 200 to 1,000 degrees Fahrenheit. The runoff pipework is designed with deliberate bends and turns to accommodate the expansion between two fixed points, that is, the boiler outlet and turbine inlet. The pipe hangers and supports are designed to be flexible and allow movement of the pipe under expansion forces. The operator should make himself aware of the normal position of critical pipe hangers. Often an indicating pointer is fitted to allow this. If a hanger does become jammed and prevents the free movement of pipe, physical damage may occur to the pipe itself or to other supports. The reheat piping system runs from the turbine back to the boiler and then once again returns to the turbine. This system operates at much lower pressure than the main steam, say 500 psi. In other respects, the pipework is similar, with high temperature insulation and accommodation for expansion. Care must also be taken that correct drainage procedures are carried out to prevent any possibility of water induction into the turbine during startup. Right, let us now move on to look at the extraction steam system. We have already mentioned that steam is extracted at various points along the turbine and used for feed water heating and perhaps for industrial process work. Here is a simplified arrangement where we show just 4 stages of feed water heating and therefore 4 extraction lines only. The extraction steam lines operate at much lower pressure than the main steam. In fact, in the case of a condensing turbine, the last stage of extraction will operate below atmospheric pressure. In this particular scheme, we have 2 low-pressure closed heaters, 1 de-aerator and 1 high-pressure closed heater. We'll be talking more about the heaters later in this module. Each extraction steam line is fitted with an isolating valve and a positive closing non-return valve, which trips to close when the turbine trips or is shut down. You will remember that we discussed this in an earlier module. Just as in the case of the main steam line, we must be careful to make sure that any condensate forming in the extraction lines will be removed via the drain connections, which are fitted at the low points of the pipe run. But where can these extraction lines drain to? Well, remember, during startup, all of the turbine and extraction pipe work is under vacuum conditions. So it is obvious that the drains cannot be opened to atmosphere. Otherwise, we would be drawing air in instead of blowing condensate out. Instead, these drains are discharged to the shell side of the condenser, which of course is also under vacuum. Often these extraction line drains are fitted with steam traps, which discharge automatically into the condenser. However, during startup, it is good practice to open the trap bypasses to make sure that all of the water is drained from the line. On large turbine generator units, the feed water pumps are sometimes driven by steam turbines using extraction steam or cold reheat steam. The discharge from the turbine drive may then be piped to a lower point of extraction for further heat utilization. Alternatively, it may be piped to the condenser so that the condensate may be recovered even if the latent heat is lost to the cooling water. In some plants, extraction steam may also be used to supply part of the auxiliary steam demand. For example, in this particular arrangement, steam can be supplied to the air preheater in the FD fan duct from either the first or second stage of extraction, depending upon the pressure available. Please bear in mind that as the load on the turbine generator changes, so does the steam flow through the turbine. with the result that the pressure changes on each extraction point. But referring back to our preheater, how can we heat the incoming air during startup when there is no steam passing through the turbine and consequently no extraction steam available? Well, in this case, a third supply of steam is available from the auxiliary steam system. Each of these control valves automatically opens in the correct sequence. That is, 1, the auxiliary steam supply during startup, 2, the first stage steam extraction during low load, and 3, the second stage steam extraction at high load. So what other sources may be used to supply auxiliary steam? Well, one common method is to use saturated steam from the boiler drum. This feeds through a reducing valve to provide steam at about 200 psi on the auxiliary steam header. Other boilers may also be selected to provide auxiliary steam to the header. The use of saturated steam from the drum is quite adequate, as its temperature of about 500 degrees Fahrenheit will provide sufficient superheat at the lower pressure. From the auxiliary steam header, steam is piped to various applications, such as de-aerator standby steam, oil burner atomizing steam, fuel oil heating. These are just some examples. The actual steam auxiliaries will depend upon the type of installation. Soot-blowing steam for the boiler is usually taken directly from the boiler itself, either from the drum or the first stage of superheat. For the turbine steam auxiliaries, such as the air removal steam ejector and gland sealing steam, a direct supply is usually taken from the main steam line before the stop valve. This high-pressure steam then passes through a reducing station to bring the pressure down to, say, 150 psi. Because of the high temperature of the main steam, a de-superheating station is also included to lower the temperature of the turbine auxiliary steam to about 500 degrees Fahrenheit. Where reducing stations are installed, it is important that one or more safety valves be located downstream to protect the low-pressure pipework in the event that the pressure-reducing valve fails and exposes this piping to the high-pressure steam directly. In some cases, the auxiliary steam piping has to travel considerable distances, for example, to an oil tank farm. There is a tendency for heat to be lost from the pipework, even though it is insulated, and the steam temperature rapidly falls to saturation and condensation begins. For this reason, steam traps are located frequently throughout the auxiliary steam system. The operator should regularly check that the steam traps are functioning correctly, that is, to discharge condensate in regular bursts. If the steam trap is not sealing properly, it will pass steam continuously and so be a source of considerable waste. Conversely, if the trap remains closed, then condensate will accumulate inside the auxiliary steam piping. In this case, we will probably be made aware of the problem by water hammer in the pipework. This occurs as the water flashes into steam intermittently. The water hammer can produce considerable mechanical movement and shock to the steam pipework and may result in broken hangers and supports, as well as leaks at valves and other equipment connections. In operating any of the steam systems, one of the most important operating requirements is to make sure that the system is maintained free of water. In this segment, we have looked at typical steam systems, but of course all plants are different. Make sure that you become familiar with all of the features of your various steam systems. That is main steam, reheat steam, extraction steam, and auxiliary steam. Now at this point, it's time for a break, so please switch off the tape and review this material in your workbook. You'll remember at the beginning of this series, we looked at the basic closed cycle of the thermal power plant. We noted that the function of the condensate and feed water system is to collect condensed steam, that is, condensate, from the condenser and return this to the boiler as feed water. The condensate collecting in the bottom of the condenser will ideally be at the same temperature as the steam exhausting from the turbine. In this situation, it is only the latent heat that is transferred from the steam to the condenser cooling water as the steam condenses. The actual temperature of condensate in the hot well is probably within the range of 80 to 100 degrees Fahrenheit, depending upon the vacuum in the condenser, and this in turn is dependent upon other conditions such as cooling water temperature. By the time this condensate enters the boiler as feed water, the temperature will be in the region of 400 to 500 degrees Fahrenheit, thus requiring less heat to be added in the boiler. During its passage from the condenser hot well to the boiler feed water inlet, the condensate receives heat from a number of sources. Initially, a small amount of heat is picked up as the condensate passes through the steam air ejector condenser, and from here through the gland steam condenser. In both cases, this heat recovery improves efficiency as it condenses ejector exhaust steam and leak-off gland steam. The condensed steam is then routed back to the condenser hot well. A drain cooler is often located here and uses condensate to extract heat from water returning in the heater drains. The condensate then passes through several feedwater heaters where heat is added by extraction steam. In this particular scheme shown here, we have two closed type heaters and one open heater where the extraction steam comes into contact with the condensate. This vessel is known as a de-aerator, as the mixing of steam and water liberates any dissolved gases, principally oxygen, from the water. We'll be talking more about the construction and function of feedwater heaters in the next segment. The pressure inside the de-aerator varies with the extraction steam pressure. At full load, this is likely to be, say, 150 psi. However, at lower load, this pressure would be considerably lower. Often, the de-aerator is located at a high elevation in order to provide a positive pressure to the suction of the boiler feedwater pump. The boiler feedwater pump draws condensate from the de-aerator and pumps this through further closed feedwater heaters, one in this example, and on into the boiler. We have, in fact, two pumping loops to transfer the water from the hot well to the boiler. First, the condensate pump pushes the condensate through the coolers and closed feedwater heaters and up into the de-aerator. In order to achieve this, the condensate pump must operate at a pressure of about 250 psi. This part of the system, as you would expect, is known as the condensate system. From the de-aerator onwards, we refer to the continuation as the feedwater system, which operates at much higher pressure. The pressure developed by the boiler feedwater pump must be sufficient to overcome losses in the piping system, plus the pressure in the boiler itself. This means that the boiler feedwater pump discharge pressure must be about 2,000 to 3,000 psi, depending upon the particular installation. The feedwater pump may be driven by an electric motor or a steam turbine. The steam turbine has the obvious advantage of variable speed control, which can be used to adjust the quantity of water being supplied to the boiler. Of course, the same result can be achieved by applying a variable speed hydraulic drive between an electric motor and the pump. The ability to control the quantity of water being pumped into the boiler is vital for safe boiler operation, and the control system must be able to respond rapidly to changes in water level in the boiler caused by variation in turbine load. One of the most common forms of boiler feedwater control is effected through a modulating feedwater control valve. This valve is usually operated according to signals from the boiler control system. In order to provide finer control at low loads, a small bypass is usually fitted, complete with a control valve. The two valves operate together in response to signals from the boiler water level control system. During startup and at low load, the small control valve is operated. Eventually, as load increases, this valve approaches the full open position, and the large valve takes over the operation. A further bypass may be fitted around both of these valves for use in case of failure of the boiler control system or valve actuators. This manual bypass is usually operated by a remotely controlled motor actuator. With the arrangement shown here, a potential problem could arise during normal operation if both control valves were to close, perhaps due to a high water level in the boiler drum. In this case, there would be zero flow of water through the feed water pump. And as the pump is continuing to rotate, the temperature of the water would rapidly increase and start flashing into steam. This could cause considerable damage to the pump internals. In order to prevent this problem, a recirculating line is fitted to the pump discharge. In the event that the feed water flow through the pump falls below a preset minimum, the recirculating valve opens automatically and passes water directly back to the de-aerator, thus maintaining the pump in a safe operating condition. In many power plants, 2 boiler feed water pumps may be installed, providing 100% standby. An alternative to this arrangement is to provide 3 50% pumps. The standby pump may be made available for automatic start in case of failure of the running pump and a decrease in feed water pressure. The feed water pump is truly the heart of the power plant cycle and therefore must provide 100% reliability in supplying high-pressure feed water. Make sure that you're familiar with all the mechanical details of your particular feed water pumps and especially the procedures for making the pump available. For example, on the standby pump, you will typically need to make sure that the inlet and outlet isolating valves are open. The pump is fully charged with water and all air has been vented. The recirculating line isolating valves are open. The recirculating line control valves should be open as there is no flow passing through this standby pump. Sealing water is being supplied to the glands. Cooling water is being supplied to the bearings and the lube oil cooler. The forced lubrication system must be available for service with the correct amount of lube oil in the tank. The balance piston leak-off line must be open if installed. The purpose of this line is to help balance the axial thrust of the pump impeller. And the driving motor must be ready for operation with the breaker racked in and power available. Your particular pumps may have other requirements. Make sure that you're familiar with all of these procedures. As well as providing feed water for the boiler, the feed water system provides water for the de-superheaters, that is, on the main steam and reheat systems. De-superheating water is tapped off the feed water system at a point fairly close to the feed water pump. The reason for this is as follows. A sufficiently high pressure must be available in order to force the de-superheating water into the steam systems. The temperature of the water should be such as to provide cooling action. Therefore, it should be taken before feed water passes through the high-pressure feed water heater. We have mentioned earlier that some losses do occur on the closed cycle system, and therefore a certain amount of make-up water is required to compensate for the loss. The make-up water is of high quality, produced in the demineralizers or evaporators and stored in the condensate tank. For make-up purposes, the water is usually fed into the condenser. During operation, the vacuum in the condenser steam space causes water to flow from the condensate tank due to the difference in head. But how does the system know when and how much makeup to add? In fact, how is the level of condensate controlled in the condenser hot well? Also, how is the level of condensate controlled in the de-aerator? This simplified diagram shows how these objectives are achieved. Makeup water from the condensate tank is drawn directly into the condenser through this modulating control valve, which in turn is adjusted according to the level transmitter which is located at the hot well. In a similar manner, the flow of water into the de-aerator is determined by this particular control valve, which is controlled by signals from the level transmitter at the de-aerator. Let's see how this simple arrangement works during a plant shutdown. As we begin to reduce load on the turbine generator and boiler, we find that the level in the de-aerator begins to fall. The reason for this is that as the production of steam is reduced, a certain amount of shrinkage takes place in the boiler. Consequently, the boiler water level control system draws more water from the de-aerator. This in turn causes the de-aerator control valve to open up and so draw more water from the hot well. As the level in the hot well falls, more water is drawn from the condensate tank. When load is increased, the opposite situation takes place, as the boiler water level increases due to swell. In this case, the boiler feedwater control valve reduces flow, the de-aerator level tends to rise, so decreasing the de-aerator control valve opening. This causes the hot well level to rise, thus causing the makeup valve to close completely. If the hot well level continues to rise, we must find some means of dumping this excess condensate back to the condensate tank. This is achieved by fitting a connection from the condensate system through a control valve back to the condensate tank. This is known as the overflow control valve, and its opening is determined by high water level in the condenser hot well. The level control system we are studying here is one typical example, but you must make sure to study your own condensate and feedwater system. Now, we still have a lot more to say about the condensate and feedwater system, but first, let's take a break to review in our workbooks what we've covered so far. For now, please switch off the tape and review this material in your workbook. When you walk around your own condensate system, you'll notice a large number of connections to various pieces of equipment. Let's look at a typical arrangement. Soon after the condensate pumps, we notice small piping connections to the chemical feed system. This allows us to fill the chemical feed tanks and mix additives such as morpholine, hydrazine, cyclohexylamine, and other products for subsequent injection into the condensate system. We will also see connections to supply condensate to the gland steam, de-superheater, and to the turbine exhaust hood sprays. We also note here a recirculation connection which passes condensate back to the condenser through a control valve. This connection is used during startup of the turbine to ensure a constant flow of condensate through the ejector condenser and gland steam condenser. This is necessary because during the initial stages of startup, there will be no feedwater flow to the boiler and consequently no condensate flow to the de-aerator. Later, as condensate flow increases, the flow measuring element signals the recirculating valve to close. Note that all of these control valves are equipped with a manual bypass to allow some manual operation in case of failure of the control system. In actual fact, this would be difficult to manage, but it would at least allow us to perform a shutdown in reasonable safety. One other important connection in the condensate system is from the condensate fill pump, which is located adjacent to the condensate tank. This fill pump provides sufficient pressure to allow us to add water to the de-aerator or the condenser when the unit is off load. In this condition, of course, there would be no vacuum in the condenser to draw water from the condensate tank. Now, at this point, let's turn our attention to the feedwater heaters. In our earlier example, we looked at a system which contained 4 stages of feedwater heating. However, it is quite common to have 7 stages and even more. Moreover, in large plants, each stage may consist of 2 feedwater heaters. However, in all of this, the principle of operation is the same. So we will continue our discussion by looking at the 4 stages of extraction. There are 2 basic types of heat exchanger used in the feedwater system. That is, the closed type and open type. For example, the 2 low-pressure heaters shown here are of the closed type, meaning that the condensate passing through the heater does not come into contact with the extraction steam, which is providing the heat. Closed feedwater heaters may be constructed in the vertical position like this, or horizontally as shown here. In either case, the internal construction is similar. This type of heater is known as a tube and shell heater. Water enters at one side of the water box and passes through U-shaped tubes to exit at the other side of the water box. The condensate is pushed through the large number of tubes, typically about 300, by the pressure on the condensate pump discharge. The tubes are supported and held in place by internal baffles. Extraction steam enters the shell and fills the space around the tubes, consequently giving up heat to the water passing through the tubes. The steam condenses and falls to the bottom of the heater from where it is drained, passing through the heater drain system back to the condenser. As the steam condenses, it releases a small amount of dissolved gases such as oxygen and carbon dioxide. It is important that these uncondensable gases be removed, otherwise they will collect around the tubes and provide a resistance to the transfer of heat. The gases are drawn off through the vent system, which is piped back to the condenser. In practice, vents are fitted at both the top and intermediate level of the heater. The reason for this is that air finds its way to the top of the heater, while carbon dioxide remains at the lower level just above the water level. In most plants, the venting arrangements are as shown here. You can see that the upper and lower vents from the heater join together and pass through this orifice direct to the condenser, which is, of course, operating at much lower pressure. The objective of the orifice is to reduce the flow. Otherwise, excessive steam may pass through the vent in addition to air and carbon dioxide. However, during startup, the difference in pressure between the heater shell and the condenser is not very great. Therefore, in order to make sure that the heater is well vented, a bypass valve is fitted around this orifice. This valve should be opened during startup and closed when the unit is placed online at minimum load. In the example shown here, both low-pressure heaters are vented to the condenser. Now let's take a look at the heater drains. Remember that the B heater operates at a higher internal pressure than the A heater, and this in turn is at a higher pressure than the condenser. The heater drains are therefore cascaded like this. The drains from heater B pass into heater A, where more heat is given up. The combined drains from A heater pass into the condenser. Control valves are placed in both heater drain lines to maintain a minimum water level at the bottom of each heater. The operator must always note the position of these control valves as part of his regular inspection. As you would expect, at higher loads, more extraction steam is being condensed, and consequently the control valve must be opened quite wide in order to maintain the level inside the heater. If the control valve for some reason or other becomes defective and opens too far, then all of the water would drain from the heater and steam would blow straight through into the condenser. This would be extremely wasteful, as the steam is not condensing and giving up its latent heat to the condensate. Conversely, if the valve is defective and does not open enough, the water level will rise in the heater and blanket a number of tubes, so reducing the effectiveness of the heat exchange. One highly dangerous condition that can occur is internal tube leakage. In this situation, condensate could pass directly into the shell of the heater and rapidly fill the space inside. This water could then pass back up through the extraction line and into the turbine. As we have mentioned several times before, this is prevented by the positive closing non-return valves on the extraction lines, which close when high water levels occur in the heater. In some installations, the high water level causes the condensate to bypass the heater altogether by automatically operating the motor-actuated isolating valves in the following sequence: open bypass valve and then close inlet and outlet valves. The matching of extraction steam flow to the heater and condensate flow through the heater takes care of itself automatically. As more condensate is pumped through the heater, more steam is condensed, so reducing pressure and pulling more steam from the turbine. In operating closed feedwater heaters, the operator must be sure to check that venting and drainage of the heater is functioning correctly. In the system shown here, we have another closed heater on the high-pressure feedwater side of the system. In this case, operation of the heater is similar to the LP heaters. The main difference is that the heat exchanger must be built more ruggedly to withstand the much higher pressures on both the feedwater side and the extraction steam side. As before, care must be taken with venting and drainage of condensate from the shell. However, in the case of this high-pressure heater, both the vent and heater drains are piped to the de-aerator, which of course operates at lower pressure. In many plants, this differential is insufficient at low load to create the flow of drains from heater to the de-aerator. Remember that in many plants, the de-aerator is located at a high elevation. To avoid this problem, the high-pressure heater drain can be alternatively routed to the condenser by automatic operation of control valves. Okay, now let's turn our attention to the open heater in this system, that is the de-aerator. The de-aerator actually has two functions: to add heat to the condensate and feed water to improve cycle efficiency, and to expel oxygen and other dissolved gases from the boiler feed water. The presence of dissolved oxygen in feed water is a prime cause of corrosion in boiler tubes. Removal of as much dissolved oxygen as possible is essential. And normally we try to limit the amount of dissolved oxygen in feed water to as low as 2 or 3 parts per billion. A typical de-aerator looks like this. In actual fact, the de-aeration takes place in the upper vessel, while the large vessel below is merely a storage tank providing suction to the feedwater pump. In most plants, the capacity of this storage tank is sufficient to keep the feedwater pump going for about 10 minutes, even without receiving condensate from a condensate system. So this should be sufficient for an emergency shutdown. The removal of dissolved oxygen is achieved by intimate mixing of steam and water. The condensate enters at this point and passes over a number of trays, which cause the liquid to break up into fine drops. This increases the surface area available and so greatly improves the mixing with steam. The steam condenses and, in doing so, raises the temperature of the mixture to saturation. This action liberates the oxygen which is present, and this is exhausted from the vents at the top of the de-aerator. The de-aerated water droplets then fall into the storage tank below. During startup on the unit, before extraction steam is available from the turbine, partial de-aeration is achieved by supplying live steam to the de-aerator. This comes from the auxiliary steam system and is automatically controlled. That is, when the extraction steam pressure falls below an established minimum, the live steam supply opens up. The de-aerator vents may be piped to the condenser, but frequently they are released to atmosphere through a vent condenser. In this arrangement, most steam blowing to atmosphere through the vent is condensed as it passes over the condensing tubes, which transfer heat from the steam to the incoming condensate. So much for feedwater heating. Clearly, the condensate and feedwater system is a vital artery in the operation of the power plant, providing the essential water for boiler operation and collecting condensate returning from feedwater heaters and other equipment. We have mentioned the importance of adequate venting of feedwater heaters, but venting is also necessary when filling the piping system with water in preparation for operation. All of the condensate and feedwater piping is fitted with high point vents discharging to atmosphere. When the system is being filled, it's important that the vents remain open to allow air to be discharged. When water can be seen exhausting from the vents, they may be closed. Equipment such as pumps and heat exchangers are treated similarly. Now, at this point, it's time to move on and look at cooling water systems. But before we do that, let's take a break. For now, please switch off the tape and thoroughly review this material in your workbook. As you would expect, the generator is well equipped with indications, alarms, and trips to provide protection. Alarms are triggered to warn of such conditions as high bearing temperature, abnormal lube oil conditions, high stator winding temperatures, high inlet temperature of cooling air or hydrogen, low seal oil pressure differential on the hydrogen system, low hydrogen purity, low hydrogen pressure, high rotor winding temperature, electrical protection relays tripping the unit in case of a generator electrical fault. Essentially, control of the generator is concerned with three items: control of active power or megawatt output by adjusting fuel input, control of reactive power or megavar output by adjustment of excitation, control of terminal voltage by adjustment of excitation. Let's look at active power. That is megawatt output first. This is the power which actually does useful work for the consumer. For example, you use kilowatt hours in your light bulbs and electric heaters. You pay for kilowatt hours to run your appliances. The megawatt or kilowatt is the component of power which does the work. As we know, the demand for megawatts varies throughout the day as consumers switch their electrical devices on or off. As we cannot store electrical energy, at least in large quantities, the combined power output of all of the generators which are connected to the system must exactly equal the total power demand at every instant of the day. The total power demand consists of the consumer's demand plus power system losses, which may be as high as 4 or 5%. If at any time the power demand is greater than power production, then the frequency will fall. It is the load dispatcher's job to keep system generation and load balanced. He must do this while paying attention to the economic loading of units, which means the most economical generating units should be fully loaded first. At the same time, he has to allow for limitations in the transmission system, say due to line outages. So the load dispatcher's job is quite a handful, just as much as the turbine operator's. However, he is assisted by computer programming and by automatic devices such as the turbine governor and the dispatcher's automatic generation control system, known as AGC. We mention all this as background so that you can appreciate the dispatcher's urgent appeal to you on occasion for either a rapid increase or decrease of unit output. We know that in order to change the generator's active power output, we must change the energy input, that is, the steam flow through the turbine. This may be performed in several ways: manually by the operator in accordance with predetermined loading instructions or on request from the dispatcher; automatically by the turbine governor, which responds to changes in turbine speed, which is in turn related to system frequency; automatically by the dispatcher's AGC if this particular generator is being used for regulation, that is, to assist in frequency control. Most of the machines on the system, that is, steam turbines, gas turbines, and hydro turbines, will operate on governor control. If there is a sudden increase in system load, all of the machines immediately slow down, and this is immediately detected by the governors. Governor response opens up the fuel inlet or steam inlet valves, and so increases the unit outputs in order to meet the increased load demand. This action takes about 10 seconds to stabilize. However, it is important to note that although each governor moves to stabilize the frequency, it does not return the frequency to its original position. This is due to the regulating characteristic which is built into the governor known as speed droop. Typically, the turbine governor is set to regulate at 5% speed droop, as applied load increases from 0 to 100% power output. Of course, this situation can be corrected easily by adjusting the set point of the governor. This can be done by the operator at various intervals or by automatic frequency control devices. Usually, certain generators on the system are selected to operate as regulating units, receiving immediate signals from the AGC system to correct frequency. The objective of the speed droop setting is to ensure stable operation of generators which are connected in parallel on the power system. If all of the governors on the synchronized generators are set to, say, 5% droop, then they all share in load changes proportionally. However, we may wish to make certain units on the system more responsive to frequency changes than others. This can be achieved by setting the droop characteristic on those units to a lower value. The generator with the lower setting will pick up or throw off proportionally more load than the other generators on the system. Check with your supervisor for correct droop settings on your machines. Remember, the lower the percentage droop, the more sensitive is the governor, and oversensitivity can cause unstable operation and hunting of the unit. Now remember, all of the units which are connected to the power system are running at precisely the same synchronous speed. This is obvious because they are synchronized together, and the frequency is precisely the same at all points of the system. So how is it then that one unit may operate at, say, 100% capacity and another at 50%? Doesn't this mean that the unit with the greatest load is running faster? Well, beware of this trick question. Of course, it cannot run faster because, as we just said, the units are all synchronized together. So how does it then put out more load? Well, the answer is in the load angle, or power angle. This is the relative angle between the induced voltage due to the rotor and the terminal voltage, which is dependent upon the power system. This diagrammatic representation shows the situation at zero load. The rotor and the stator voltage are exactly in phase. If we wish to increase the load output from the unit, we add more energy to the prime mover. This initially accelerates the rotor so that it moves ahead in phase. There is now a power angle or load angle created between the rotor and the stator voltage. This in turn causes power to flow from the generator into the system. To further increase power output, we increase steam flow and so further increase the load angle, which in turn increases the power output. In each case, the rotor settles down to its new condition and continues to run at the new load angle. At maximum load, the load angle will probably be about 60 degrees. So now you can see if we have, say, 3 units in parallel on a common bus. The unit which is generating at 100% capacity will have a load angle of about 60 degrees. The unit at 50% output will have a load angle of about 30 degrees, and the unit at zero load has a load angle of 0 degrees. Okay, so much for power output of the generator. Let's now take a break, and then we'll come back and talk about voltage control, excitation, and megavar output. For now, please switch off the tape and review this material in your workbook. Control of the generator output voltage is affected by adjusting the magnitude of excitation current. We already know that increasing excitation results in an increase in the strength of the rotating magnetic field. This, in turn, brings about an increase in the voltage, which is induced into the stator conductors. Let's take a closer look at the excitation system to see how this control is carried out. First, we'll look at a simplified arrangement of the static excitation system. DC current from the rectifier is supplied to the rotor winding through collector rings on the shaft. The incoming AC to the rectifier is supplied from a dedicated transformer. The primary side of this transformer is fed from an auxiliary bus, or in some cases, the generator bus itself. The sine wave for the incoming three-phase AC voltage, which is applied to the rectifier, will look like this. After rectification, the DC output can be represented by this curve, and this may be further smoothed to look like this. The level of DC voltage can be adjusted by controlling the firing of a thyristor-type rectifier. The firing circuit is controlled by the field voltage regulator. This regulator has two inputs, manual and auto. The manual control disconnects the automatic function and allows the operator to directly control excitation. However, when the generator is in operation, the field voltage regulator is usually controlled from the auto position, that is, from the AC voltage controller. This controller monitors the generator bus output voltage through VTs and automatically adjusts excitation to maintain the set point voltage. The operator can adjust this set point and thus exercise control while the excitation system is operating in auto. All of these components of the static excitation system are normally located in the excitation panel close to the generator. Of course, the auto and manual control inputs are also located on the operator's panel. Another type of excitation system often used is known as the brushless exciter. The exciter is actually a small AC generator which is built on the end of the generator shaft instead of collector rings. In this exciter, a stationary magnetic field is provided from the DC winding which is wound on the stator. The rotor winding produces AC voltage, and this is fed directly into diode-type rectifiers which are built into the shaft. So we have, in effect, a rotating rectifier. The DC output from the rectifier is connected directly to the main rotor winding through leads which pass inside the shaft. There is no need for collector rings or brushes. Control of the DC excitation current is affected by adjusting the strength of the exciter magnetic field, and this is done by controlling the DC current flow through the field winding. This DC field current is supplied from a rectifier which is located in a nearby cabinet. Of course, this rectifier is much smaller than the static rectifier that we previously studied because it is only supplying field current to the rotating exciter. However, control is effected in the same manner, that is, by adjusting the firing of the thyristors, and this in turn is governed by the field voltage regulator. The arrangement at this point is similar to the static exciter. When in auto, the field voltage regulator receives its command signal from the AC voltage controller, which in turn monitors the output voltage of the generator. The operator can adjust the AC set point as required. When starting up the unit, the field voltage regulator may be set to manual, and in this case, the operator will control the regulator directly. So what is the effect of adjusting excitation? Well, obviously, one effect is to adjust the output voltage of the generator. For example, by increasing the excitation current, the generator terminal voltage will increase. But that's not all that happens. As terminal voltage is increased, the generator will produce and transfer more megavars into the power system. On most units, the megavar output of the generator is indicated right alongside the megawatt output. The term megavars stands for megavolt amperes reactive, which is actually the unit of measurement for reactive power. But what is this reactive power? Well, it is a fact of life that all electromechanical devices, such as transformers, motors, electromagnets, and so forth, require megavars in order to set up and maintain their magnetic field. For example, let's look at an electric motor. The shaft on the motor rotates to drive a machine and produce useful work, let's say 100 horsepower. The motor will need to draw about 75 kilowatts in order to produce this power output. But in addition to this, the motor will need to draw about 30 kilovars in order to set up the magnetic field which is needed for the motor to function. So on our power system, we have a demand not only for active power, that is megawatts, but also for reactive power, or megavars, and both of these power components must be supplied by the generators. Fortunately, the provision of megavars does not require any increase in energy input to the turbines. The fact is, reactive power does not absorb any energy at all. The reactive power actually oscillates twice per cycle between the magnetic field of the generators and that of the consumer's equipment. The average power consumed is 0. So why are we concerned about this reactive power? Well, the problem is that even though increased energy input is not required, increased current still flows through the generator windings and through the power system. The result of this is that we could easily overheat the generator windings if we had a high megawatt output plus a high megavar output. Definite limitations are placed upon the combined total output of megawatts and megavars. Megawatts and megavars act with different phase relationships to voltage. Active power is in phase, while reactive power acts 90 degrees out of phase. The combination of megawatts and megavars is known as MVA, that is, megavolt amperes. You will remember that in a DC circuit, if we multiply volts times amps, we get power in watts. However, in an AC circuit, volts times amps, VA, gives us apparent power, as it is a combination of vars and watts. The ratio of true power, that is active power, megawatts, to apparent power, MVA, is known as power factor. This generator capability curve shows us the limitation on MVA due to current in the stator. For example, at this megavar loading, we can only produce this amount of active power to stay within the machine's capability. Clearly, in order to keep within the MVA rating, we must reduce megawatt output if we wish to produce a large output of vars with the generator. However, there are other limits to observe in generator operation. As we know, in order to increase the megavar output of the generator, we must increase excitation. The increase in excitation current flow increases the heating of the rotor winding. This curve shows the limitation due to rotor heating. You can see that we can operate this generator at 180 megawatts and 0 megavars. But if we needed to produce, say, 100 megavars, then we would have to reduce the active power output to 140 megawatts in order to keep within the established rotor heating limits. We also run into trouble if we reduce excitation too much. In this case, as the voltage falls, vars will flow into the generator from the power system. This is shown on this curve as negative vars. The problem is that if the rotor current is reduced too much, the magnetic field may become so weak that the generator will lose stability and fall out of synchronism with the other units on the system. In order to prevent this, a minimum excitation limit is established, which is given by this additional curve here. This combination of limits provides the generator capability curve that you should be familiar with. For each specific generator, this curve is normally displayed in the control room. Make sure that you always operate the generator within these limits, whether you are supplying megawatts and absorbing or supplying megavars. Okay, now that we have you interested in this subject, I have to point out that any further discussion is really outside the scope of this program on steam turbines. If you would really like to know more about electrical system operation, please refer to our other programs. Most power companies already have our programs on power system operation, power system protection, and others. At this time, please switch off the videotape and thoroughly review this material in your workbook.